So, hello everyone. So our next speaker is Salim Alloun. He will speak on cohomological representations of the automorphism group of dessin, denfant.
Denfant, yeah, right.
Thanks.
Okay, so thank you very much for giving me the opportunity to give this talk. So it's my first talk and first time in India. So just I have to say that it's hot in India for the weather and for spicy food. Okay, so here we are. So we already have talked a little about dessin d'enfant with the talk of Nakamura. But here we are really going to be to follow the philosophy of Grothendieck, who is really to say that you have combinatorial objects and the absolute Galois group acts on that, and the goal is to really give a geometric description of GQ. So of this action, okay. And just a reminder is that so the thing that really struck Grothendieck is the fact that every smooth projective curve defined over Q bar can be realized as with a dessin. And so that's really important because if you take, for instance, so a genus zero curve, then it's completely empty because you only have P1. If you take a bigger, okay. So it's okay because you only have P1. If you are in genus 1, then you can, for instance, take a Weierstrass equation. That gives you parameter to describe the curve. And if you are genus 2, Pierre reminds us that every curve is hyperelliptic. But in a general case, you can give equations like a general description. So that's really important to say that, okay, maybe that's completely out of reach for now, but that you can describe any curve with something that's completely combinatorial. Okay. That's interesting because I read a book of Munford that begins especially by saying that that's the problem, that in the genus case, if you, yes. Okay, so the reminder of the object that we are looking at. So we have three categories. So this we have already seen is the category of ramified cover of P1, étale outside of 0, 1, infinity. And X is a smooth projective curve defined over Q bar. And this category is equivalent to, so here I take P1, the fundamental group, as we have already, so the group on 3 on 2 generators. Here you have finite set, so P1 acting on finite set, and the action is transitive. And here we have bipartite graphs embedded in a compact Riemann surface, and that will be the combinatorial object, the dessin. Like, that's where the word comes from. So how do you go from one category to another? Here you have your cover beta, and you take the pre-image of the segment 01. So Pierre Deligne calls it le droit chemin, and that gives you an embedded graph. And here the pre-image of 0 are the black vertices, the pre-image of 1 are the white vertices, the pre-image of infinity will be the faces of your graph. And you can also label the edges by taking a point on 0, 1 that will be not ramified. So take, for instance, 1 over 2. And so that gives you the embedded graph, okay, in the curve X. And how do you go from here to there? You have the action of the fundamental group on the pre-image, as always, of one generic point outside of 0, 1, infinity, and just take 1/2. And that means you can see this set as a set of edges of your graph, okay. And so By a dessin, I mean so an isomorphism class in one of those categories. Okay, so we know that GQ acts on the set of dessin, and Nakamura gave us the proof that the action is faithful, but you see that his proof was not like really something geometric. You only act on the J invariant. You take a G-1, so elliptic curve, and you only act on J invariant. So you only change the curve, and I mean it's like just a GQ acting on algebraic number. But in fact, there are other faithful actions. You can make act GQ only on trees, so that will be on genus 0. So that was proved by Schneps-Lenstra in 1994. And also, you can act on regular dessin. So what does it mean to be regular? To be regular mean that the cover is Galois. And so that was proved by Pierre in 2014 and independently by Gonzalez, Diaz, and Jaikin Zapirain in 2015. Okay. So now when I have this, when I take a dessin, okay, so let D a dessin. I note by G will be the quotient of this action. Okay, so that will act on the bijection of the set, let's say A. Okay, A as here, and the automorphism of D will be the automorphism of the cover. Okay, so just those arrows that make the diagram commute. Okay. So now, if I take, okay, and if I, and also just a formula, if I have the Riemann-Horowitz formula. So if I take the genius of X will be 1 plus 1/2 times D Lx Ly and Lz, and it's just the number of preimages of 0, number of preimages of 1, and then number of preimages of infinity. Okay. Okay. So now, when I make acts, so I take D, and I can take the stabilizer of D inside GQ. Okay, because okay, so the stabilizer by the action of GQ on the set of dessin. And so I define, okay, so the moduli field of D is MDT, which is defined by the Galois correspondence, so by Galois Q bar MD of D, which is okay, the stabilizer of D. So for instance, the degree of this field will be the number of conjugates of your dessin, okay? But in fact, so that's the main, object that we want to compute, given a dessin. And just a reminder that this moduli field is different from the field of definition. Because of course, the moduli field is included in the intersection of all fields of definition, but that doesn't mean that the intersection of all fields of definition is a field of definition. So that doesn't mean that the moduli field is can be a field of definition. And by the way, there are an article that from 1997 of Deb and Doué that gives like a proper condition for the moduli field to be a field of definition. And just to give you an example, there is a paper of Molyakov, 2023, that gives an infinite family of genus 1 dessin, such that the degree of the field of definition, of any field of definition regarding the moduli field tends to infinity. Okay, so in a general case, I think that in the genus 0 case, you can always take an extension of degree 2. I'm not sure, but in general case, it goes to infinity. It can go to infinity. But in fact, the thing is that here we consider D as a cover, okay, in the category of cover, but you can also refine and give other moduli fields by looking at this tower of field. I will write it and then I give the definition. So here you consider D as a cover, okay, as I said before. Here you consider only, so C for a curve, you only consider the curve that, because when you take a dessin, it fixes the curve, the isomorphism class of the curve. And then you can, and of course, if you fix the cover, then in particular, you fix the curve. So the moduli field of the curve associated to D will be a subset of a subfield of this moduli field. And here you consider, so here you consider the category as we said before. So just as a cover. Here you forget about the cover, you only take the curve X. And here you take the cover, but given with the action of automorphism of D, okay? Because the automorphism of D will be, X is defined over Q bar, so the automorphism will be defined over Q bar, and you can make also GQ, make act GQ on the automorphism. So that gives, of course, this inclusion of fields. No, it's like automorphism. Automorphism, dessin, and curve. Here it's curve, because you only take the curve. You forget about the cover. Okay, and how do I? Why I'm interested? Yes.
An action of some semi-direct product of stab and out on the objects of the middle level.
I mean, it's just that when you make act GQ, you make act on the equation that defines X and on the coefficients that define the cover. And here you make also, it acts on the coefficients that define the arrows of automorphism. Okay, so. But, no, I don't see, no. But then I will give example of, okay, and why I came to this, this moduli field is because there is this Parker's conjecture that you can find in a paper of Harbater in 1984. And the thing is that he proposed some endomorphism, and you saying that if you take the eigenvalues of this endomorphism, it will give you this field, this moduli field, and not this one. So that's why I'm interested. I defined that moduli field. Yes. Yes. Yes, G cover. Yeah, right. Sorry?
What's the definition? Moduli field for a G cover?
So the definition is that.
It's not field definition.
No, it's not field definition. It's never field definition. Yeah, yes. It's just like you act on the automorphism, which are defined over Q bar, and you say, are they isomorphic? But it can happen that this will be equal to Q, but the automorphism are not defined over Q.
You don't fix the automorphism.
The action. Okay. Okay, so now I will get completely to the title of my talk. Okay, so just to give notation, if I take R a ring and A a set, I call RA will be the free module over R with basis EA, okay? And then, of course, if I have G that acts on A, then I can make act G on R of A by just making G EA equals E GA, just that natural definition. And now, if I have a dessin, I just define, and so K a field, I just define K like this would be just you mod out by the invariance. And D will be, D here will be the number of elements, so the number of edges, the size of A, also so the size of, the degree of beta, sorry. And, okay. And so if you are in a, so if you are in a case of D, so if D is regular, then G acts freely on A, so you can identify A with G, okay? And in fact, so the action of G on A will be left multiplication, okay? So G acts on A equals G by left multiplication. And automorphism of D will be equal to G, and it acts on G by right multiplication. Because in general, the automorphism will be the centralizer here. Automorphism of D will be the centralizer of G in bijection of A, and in this case, its automorphism of D is isomorphic to G, and you have left multiplication, right multiplication, of course, commutes. Okay. And just like, okay, and so now K, this G module will just be the regular representation of G minus the trivial representation. Okay. And just a last notation. Here I have EA, and I just call A with brackets to be EA mod mod the invariant. Okay. Okay. Okay, so now where does the cohomological aspect come? Is from, okay, there's a proposition. So I'm just, for simplicity, take L to be K of D, okay, just for notation. You have this exact sequence of odd of the module. Exact sequence. Okay, so when I mean out of D modules here, out of D are arrows between, so from X to X, so you can so it induced arrows between the H1, okay? And here you have to consider that out of D is G. So I mean, at least out of D acts on A, the preimage of your generic point. It also acts on this module, okay, with this exact sequence. And so the point is that, and so now if I have a characteristic of K that does not divide, let's say, the cardinal of G, then I can just compute, just have a supplementary, I call that supplementaire, like this. And so here it will be isomorphic to the H1. So the idea is to get back the H1 of your curve by giving a combinatorial description. So just to give you an example. So if I take D to be this dessin, okay, so of course, if I am drawing genus 0 dessin, then H1 is 0, so it's not interesting. So here it's an elliptic curve, so you have to identify the opposite sides, okay? So here it's 1, I just label the edges. Okay, so here it's also 1, also 3, also 4, and also 2, okay, the same vertices here. So now I can describe HDK to be something like with the notations that I have before. And so you have to understand this kind of combinatorial description to be, so the H1, so here it's the same as the H1. And so you have here on genus 1, you have two loops that generate the H1. And so here you have this loop, which is to follow the path 1, then 3 in the other direction. And so that gives this loop. And here this loop will be 2, then 4 in the other direction. Okay? So you label, you think of every edges to be a path that goes from the preimage of 0 to the preimage of 1. Okay, to have orientation. And just another example. And so here you will have H to be so I mean it's basically the same thing. Just follow the path and that gives you this loop and this loop. Okay. And just for your just to note, this is the elliptic curve with J invariant 8000, and this is a CM elliptic curve with this endomorphism ring. Okay. Okay. So now I will also give example. In fact, to make you understand, so the point is that okay, I just reviewed the tower. Because the point is that when you make GQ acts on a dessin, I mean, you can like do the computation and say, okay, it gives me this number. I mean, two conjugates, for instance, or 3 conjugates. But what I want to understand and what my motivation is to separate with this tower. So to say, what does it make on the curve? What does it make on the cover? And what does it make on the automorphism? Because maybe it's even simpler to get this moduli field, even if it's bigger. And maybe it's simpler to get this moduli field. So I just give another example. So I take maybe the simplest case is to take G be equal to 0 over PZ. So I take X, Y, and Z elements in that, and I call tau the triple X, Y, Z. And so with the assumption that X plus Y plus Z equals 0, so that's the analog of X, Y, Z equal 1 because they are in Z over PZ. Okay. Now, if I take this curve, so I just give you the description of the curve. You send ST to S, and here you have your curve X tau P1, and so here you just desingularize and compactify. And I just put it in dots because on the points at infinity, the arrows are not well defined. Okay, but that gives you the cover, which has monodromy group Z over PZ, and with the triple XYZ. Okay, that you have chosen. And so the genius of this curve is P minus 1 over 2. And the thing is that if you take K, so I call this dessin d tau, okay? So the module that I have defined will be, in fact, because it's a regular representation of Z over PZ minus the trivial representation. So it will be the sum of, we know the representations of Z over PZ, just the characters, and you put them together by, so chi I is the dual of chi minus I. Okay, that's the how can I say that? That's the motivation to say that this kind of module, at least a part of this module, give you the H1, because in fact in this case, the example here it's 0. Okay, so in fact here, okay, I forgot to talk about that, but if you use the Riemann-Horvitz formula here, so here you always have K to G, and here you have K. If you just use, you can compute also the dimension of that. Here it will give you K to the D minus 1, which is the same as L. Okay, and so the thing is that no, what I want to talk about is so when you have the H1 and you consider just here so I want to say X, of course, is the topological X. Okay, is the Riemann surface. When you have the Riemann surface, the H1 is always comes with the symplectic form, which can be defined by the curve product, or it's also the same as the intersection number. Okay, so you have two loops. So for instance, on the on a torus, you have gamma 1 and gamma 2. If you have chosen your orientation like that, then the curve product gamma 1 gamma 2 will be equal to 1. Okay, so just does the symplectic form that you define on the H1. But here we want to make Galois act. So if you have just like because here the curve product will be with values in K, but I mean K is a field. You can, for instance, take a finite field, and you cannot make act a GQ on that. But there is something that has a natural GQ action, is the veil pairing. Okay, so I'll just define the veil pairing, and I'll take just an example that will be only on genus 1 curve, so on elliptic curve. So you take and you consider it as an abelian group by taking a rational point. Then you can look at the p torsion points. And that gives you an arrow. So the veil pairing is an arrow from this product to mu p, which is Galois invariant. So, but by making GQ for GQ to act on that, you have to fix the curve. So you take let's say k. So k will be q of g, and g will be the J invariant of E. And so you have, if you have sigma in Galois Q bar over K, then you can make it act on the P torsion points. And you have that EP of P sigma M sigma will be equal to. Okay, so, but the fact is that now when you have this, what you want is to compute this. So why I'm talking about the P torsion points is because E of P can be considered as the same as it's isomorphic to the H1 of X by looking at the coefficient in Z over PZ. Okay, just like you can take the picture of the square, and you will have, if you take the P equal 2, you have the P torsion points here, the four two torsion points. Okay. And so now the thing is that if I take D a dessin d'enfant, so I want to compute the veil pairing, because here I give it for the case of elliptic curve, but in general you have to take the Jacobian. But for an elliptic curve, the Jacobian is the same as the curve. And so here you want to have an arrow from here to mu p, but you can't do that. So just here, you with this, which is like a cohomology of group, you also can take the curve product. So it gives you something. So let's say here I take FP. Just rewrite clearly. And here you have a dessin which is a Galois conjugate. So I can only go to FP. I wanted to go to mu p, but I can do that. If I can do that, that means that I know the structure of the curve, and a priori I don't know it. So here I will go to FP. But then what happens is that if I want to make this kind of diagram commute, here I will have multiplication by chi p of sigma, okay? Because the action here on EP will only be because we have a p roots of unity here. So here, of course, it's the p roots of unity. And the action here is just exponentiation by chi p of sigma. Chi p is a cyclotomic character of degree p. And so that means that here, if I take FP, it will be multiplication by chi p of sigma. So I don't have like a result to compute this map. So just a reminder, if here I take sigma that should fix the curve. Okay, so I should have x sigma isomorphic to x. Okay, so that means that in the tower here I have to fix this modulation. Okay. And so the thing is that, of course, if you know d sigma, like you have the triple of permutations, then you could compute this arrow. But you can imagine that this arrow will be easier to compute than just to compute the whole dessin. So And so the thing is that you could like verify if D and D sigma, so you have D and other D prime, and you want to verify that D prime, can it be D sigma? Can it be a conjugate of D? And with this kind of stuff, you can, with the assumption that you fix the curve and maybe some assumption on sigma by this economic character, then you could say, okay, are there conjugates or not? But, and of course, here I written also only for FP, but you can write it for all the P to the n torsion points. And just maybe a final aspect I want to talk about is just another example, because here, okay, here the cover is defined over Q, and the equations are also defined over Q. So GQ will act trivially on the cover, on the cover. But here, the automorphism here, okay, the automorphism of d tau will be in fact just like multiplication by roots of unity. Okay, so that's mu p. And so here, in this case, you have those modular fields are both equal to Q, and everything is on the automorphism. Okay. And by the way, if you take the eigenvalues here of the representation, that will give you that will give you a Q of I mean in this case you have MA of d tau which equals to Q of zeta p, which appears here. Okay. And so just the last example is you take and just it will be an example where the action of GQ will be only on the curve. So you take the cover to be x to the p. Okay, so the dessin looks like this. So the same thing here, you have to identify the both opposite sides. Okay. And if you label, okay, 1, 2, here k, p plus 1. E and p plus k. Okay. And here you will see that, so just have h of dk here will be isomorphic to same thing as before. Okay, so you take those two loops, but here the action of Galois will only act on the curve, and in a sense you will see that if you want to describe it like combinatorially, it really like disconnect the edges and reconnects them in other way. Okay, so that will, because here when you make acts, it changes the roots of unity, so it will change here. So in this case, you really have the GQ action. You can see it like combinatorially how it changes the curve. Okay, and sometimes you can see it as it doesn't change the curve; it only changes the cover. And so that's what I want to do in what follows in my research, is to make like this kind of description to say how can we combinatorially describe what does it make on the curve, what does it make on the cover, and what does it make it on the automorphism of the dessin. Okay, so I'm done.
So any questions or comments?
If you're given a dessin, how do you compute the curve? That is, how do you compute J? So you said J was 8,000.
Yeah, I mean, okay. So here I really have the it's in the Johnson-Wolford book. You have like the equation for the curve and for the cover, and you verify that it works. But I mean, there is no like general procedure. But yeah, I mean, it's really surprising that if you have a dessin, it fixes a J invariant. And I mean, there are a lot of questions like, how can you say that the J invariant is rational? How you can say that it corresponds to a modular curve, for instance, or mean, but that's open questions. I mean,
Yeah. So, any question? If no, let's thanks the speaker again.